Okay, so I'd like to welcome you all to another edition of Quantum Computation and Isolation. And I have the pleasure this week of introducing Professor Steve Flammia. So he got his bachelor's degree in physics and a bachelor's degree in mathematics from Penn State University in 2002. He got his PhD at University of New Mexico in 2007 under Professor Carlton Caves. He was in a postdoc at the Perimeter Institute from 2007 to 2010. He was in a postdoc at Caltech from 2010 to 2011. He was a principal research scientist from University of Washington 2011 to 2012. And then he was a senior lecturer at the University of Sydney from 2012 to 2015, associate professor at the University of Sydney from 2016 to 2018, and then professor of University of Sydney starting 2019. And he's currently affiliated with the AWS Center for Quantum Computing in Pasadena, California. He's the recipient of many awards, including the National Science Foundation EAP SI Fellowship in 2005, the Australian Research Council a Future Fellowship from 2014 to 2017, and the Pauli Medal of the Australian Academy of Sciences in 2019. So today he'll be talking about characterizing free-fermion-solvable spin models via graph theory. So please help me in welcoming either by unmuting yourselves and clapping or by clapping virtually, Professor Stephen Flammia.
Thank you very much, Joshua. It's always fun to give these Zoom seminars because you never have to travel anywhere. So you get to talk to your colleagues and present your work, but you don't have to deal with an airport. Okay, so that's right. I want to talk about characterizing free fermion-solvable spin models via graph theory. In this talk, this is joint work with Adrian Chapman, who just left the University of Sydney for Oxford, and Sam Ellman. So most of the work that I'll talk about is joint with Adrian, but at the end, I'm going to mention some joint work between myself, Sam, and Adrian, which is this second archive paper that you can see down here. Sam's a PhD student at Sydney. If I say the word solvable in this talk, I specifically mean solvable by free fermions, so non-interacting systems. I'm not going to talk about things that are solvable, for example, by beta ansatz in this talk. So everything, if I just say solvable, I really mean free and solvable. Okay. Oops. Okay, so what's the motivation for studying exactly solvable spin models? So mapping to free fermions is just a general workhorse method. First of all, it's mathematically elegant. It can also be a starting point for doing perturbation theory. From a more quantum computing side, there's a rich connection to complexity theory. So for example, match gate circuits, which have been studied by many authors, this is a highly incomplete list, have a deep connection to free fermions. Free fermions also appear in the so-called FKT algorithm for Fisher, Castelline, and Temperley to count the number of perfect matchings in a planar graph. There's also the sensitivity conjecture. It turns out that free fermions make a strange appearance in the solution to the sensitivity conjecture, which is a conjecture from computer science about Boolean functions. You can read more about that in this paper, reference 9 here. In all of these connections, graph theory actually plays a central role, and that's what we're going to focus on here in this talk. So in order to do that, we're going to need to take Hamiltonians associated to free fermions, or just general Hamiltonians, in fact. And for those general Hamiltonians, we're going to associate a graph. So what is a graph? It's just a collection of vertices and edges. The edges are just subsets of V cross V. And here's how we're going to map qubit Hamiltonians into graphs. So this is an example Hamiltonian. You will recognize this as an XY model with a transverse field. Okay, and I've got periodic boundary conditions here. And I've actually gotten rid of half of the terms. So normally the XY model would have XX and YY between all neighboring pairs on a chain, or in this case on a ring. And I've just dropped, for simplicity, half of the terms. So it alternates between XX, then YY, then XX, then YY. Those are the coupling terms. And I have a bunch of on-site Z terms. So this is a Hamiltonian. And now I want to map that to the graph that you see here. Well, sorry, this isn't a graph. This is just a depiction of if each one of these nodes here with the z on it is a qubit, how they actually overlap. So what we're going to do is we're going to define the frustration graph to be the graph where for every Pauli operator, and I don't mean single qubit Pauli operator, I mean a general n-qubit Pauli operator. So the Hamiltonian has vertices corresponding to the Pauli terms, and they're neighboring to vertices, or Pauli terms are neighboring if and only if the corresponding Pauli's anti-commute. So let's work out what the graph is associated to this pseudo XY model. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8 terms. And so indeed, you see that there's 8 vertices here corresponding to the pair of XX terms, the pair of YY terms, and each of the on-site Z terms. And of course, Z on the first qubit commutes with Z's everywhere else, and it commutes with Y2 and Y3, it commutes with X3, X4. So there are no edges leading over here, but of course, Z1 anti-commutes with X1, X2, and it anti-commutes with Y1, Y4, so I'm gonna have to put edges there. And similarly, X1, X2 anti-commutes with Y1, Y4, so there's an edge here, and so on. Okay, so just everywhere there's an anti-commuting term between a pair of things, I draw an edge between the corresponding Paulis. That's the frustration graph of a Hamiltonian. So now I'm gonna play a little game, and this is just to motivate a little bit of what's actually happening when we look at two different types of Hamiltonians, one that's solvable and one that's not solvable, and what might happen. So we're going to play the following game. So given a graph, for every edge, E, we're going to add a vertex whose neighbors are vertices neighboring exactly one of either V1 or V2. So exactly one of either V1 or V2. And we're going to not add a vertex if there is already a vertex with the same neighbors. And then we're going to iterate this, okay? So those of you who have thought about these things, what this game is doing is it's closing the bond algebra. So this thing is generating some algebra. And what we're going to do is we're going to iteratively generate terms by trying to close this algebra that we get from looking at the terms in the Hamiltonian. So we're not going to add this edge, okay, by rule 2. Right, and I just said this. We're going to repeat this until no more vertices can be added. So what happens when we do this for our pseudo XY model? So the XY model is in fact a solvable model, solvable by a Jordan-Wigner transform. And here's the 8 vertex thing. So let's, and here's now, I'm going to add one spurious coupling term, which is this over here. Okay, and let's see what happens if I iterate the discrete dynamics. In the solvable case, it iterates for a little while and then it stops. If I iterate this one, it keeps going and it keeps going and it keeps going, and I generate a much more complicated commutation structure at the end. So what's the difference between these two things? And can we understand something about the closure of this algebra, which is sort of visually represented here by this, complete tangle of edges on this graph? Can we look at properties of the graph itself and infer properties of this algebra that would say whether or not it's solvable or not solvable? Okay, that's what we're going to solve in this talk. Somehow these two graphs know the difference, and that's what we're going to try to figure out. Okay, so let's just review a little bit what it means to be solvable by free fermions. Let's look at this solvable Hamiltonian, and let's recall how the Jordan-Wigner transformation works. In the Jordan-Wigner transformation, we associate Majorana fermions to string-like operators. So these are tensor products of sigma z with an x at the end of a string of some length, in this case j, or we cap it with a y at the end, and we assign the fermion mode 2j minus 1 or 2j to these two Pauli spin operators. And you can see that these anti-commute, which is good because that's what we want to enforce. We want to enforce the canonical anti-commutation relations for these fermions, which you can see here. So what we're going to try to do is use this mapping and then find that when we apply the mapping, that the Hamiltonian terms are quadratic in the Majorana operators. So how does this work? Well, if I take products of two strings, so if I take gamma 10 and gamma 11 and I multiply them together, I get gamma 10 times gamma 11, which under the mapping gives me the following product. This tail of Z operators cancels, and I'm left with modulo some phase, which you have to keep track of. Y times Z is X, I times X is X, everything else cancels. So this product gives me this particular XX pair, okay? So we can do this down the chain. And if you do it, you get the following Hamiltonian. So this is a quadratic Hamiltonian in each of these fermion operators. So what we can do is we can write it as a matrix, as a quadratic form, basically, acting on this vector now of Majorana operators. And it turns out this is going to be an anti-symmetric matrix, which will be 2n by 2n, because now there's 2n fermion operators here. And when you study the solution, you find that the Majorana operators themselves actually transform covariantly. So if I act on these operators using the unitary action in the full Hilbert space, then I can rewrite this as the action of this 2n by 2n matrix on these Majorana indices to get new linear combinations. So this is a really handy trick, because if this is an anti-symmetric matrix over here, then this is generating some specific Lie group, SO2n. And what we can do now is we can use this property to diagonalize this little matrix, find the eigenvectors and the spectrum of this by diagonalizing it over SO2n. So I don't have the full unitary freedom, but I have something good enough, which is that I can, by rotating this matrix appropriately, I can block diagonalize it into 2 by 2 blocks that look like this, using things that live solely in SO2n over here. And then these are going to be the energies that I get. So I apply this covariance principle, and I look at the mapping on the full Hilbert space. And what I find is that this transformation actually maps the entire system to disconnected, it's a paramagnet now, right? So it's just individual spins after I've done this encoding, which can be excited or not. And each one has energy up to some overall rescaling of plus or minus lambda, right? Basically up to some overall factors that depend on some of your normalization conventions and how you define your Hamiltonian. But these things are effectively the energies splitting these two spin states. Right, and then the total energy is just going to be the sum of these individual energies, where these xj tell you the occupation numbers for each of the Majorana modes. Okay, so that's a review of how the Jordan-Wigner transformation works to solve these models. So it uses linear combinations of these Majorana modes to find the correct eigenstates of this Hamiltonian in this Majorana representation. Okay, but this isn't the only, so this is the classic model. The XY model is like the classic model for a free fermion solution, one of the classics. There are other models that are solvable by free fermions. Another famous example is the Kitaev Honeycomb Model. So in the Kitaev Honeycomb Model, it's a 2D model. And what we do is we put spins on all the vertices, and we couple the spins, depending on the whether the leg is blue, green, or red, whether it's sort of vertical or positive slope or negative slope. We have a ZZ, XX, or a YY coupling. Okay, so this is like a really strongly anisotropic coupling around each of these spins to its neighbors. And we can put some parameters, JX, JY, and JZ, into this model. So how did Kitaev originally solve it? There's more than one solution to this model now, but how did Kitaev originally solve it? Oh, sorry, I should say that there are some constants of the motion. So if I take the product of the links around a plaquette, so I take XX times YY times ZZ times XX times YY times ZZ, then I get the following term that you see here in yellow, ZXY, ZXY going around this plaquette. And this will commute with each of those individual bonds. So this is a constant of the motion that's local, in fact. So I can assign this to be +1 or -1, and I'll get a different equivalent sector labeled by that symmetry when I try to diagonalize this Hamiltonian. There are also some other operators that are string-like, and depending on how you define boundary conditions, if you put this on a torus, these are also going to commute with the Hamiltonian. So if I take an Lx by Ly lattice, the effective Hilbert space contains about Lx times Ly qubits in a mutual eigenspace of each of these cycles. So these sort of homotopically trivial cycles, as well as these non-trivial cycles, depending again on your boundary conditions. But this doesn't completely solve the model because there's sort of more spin degrees of freedom here than there are constants of the motion. So what you need to do is find a free fermion mapping per sector to solve the rest of the model. And how did Kitaev do this? He did this by mapping each qubit to 4 different fermions. So remember, the qubits were spins that lived on the vertices of this honeycomb lattice. So what we're going to do now is we're going to say, well, every Pauli, so Pauli at site K labeled by alpha, is going to get mapped to some phase times a Majorana operator B sub k times C sub k. And so these things are going to be labeling these 4 Majorana operators. So with this new symmetry at each vertex, we still have an overall constraint to map to a physical subspace. And the bond fermions pair up. So these 2 green ones are going to pair up to give us constants of the motion. These red ones pair up to give us constants of the motion, and so on. And we get a bunch of terms that isolate like this. And then we can solve the matter fermion Hamiltonian over each bond sector. This is how Kitaev solved the model. If you didn't follow this, it's okay. This is really not so much to study the solution of Kitaev's model, but just to contrast the solution of this model with the solution method for the XY, where it was really straightforward how to do a Jordan-Wigner transformation. And so what I'm really trying to highlight here is not the specific solution method, but just how distinct these solutions can look when you look at them superficially. Okay, so is there any unifying principle that we might find, given that these 2 prime examples look so different on the surface? So the question I want to ask is, when is a mapping to free fermions possible? And can we understand it, as we've already alluded to, just by looking at properties of the graph? So recapping our situation, we're given a general Pauli Hamiltonian. So I'm expanding it in the basis of n-qubit Pauli operators. So I've fixed a local basis for each spin, and I've done this expansion. When can we define a distinct quadratic fermion operators? When can we define distinct quadratic fermion operators such that the commutation relations are respected? So I'm looking for a mapping from these Paulis into fermionic bilinears such that Pj, Pk anti-commute exactly when the intersection between this label pair, the fermionic bilinear pair of labels, so J1 and J2 are the labels associated to J. So I want that those associated labels, if they intersect in one place, then I pick up the sign. If they intersect in both places, then this should commute. And if they don't intersect at all, then these Paulis should commute. Okay, so that's the algebra that I'm trying to respect. In graph-theoretic terms, what this is asking for is the following. When can we label the vertices of a frustration graph by subsets of size at most 2, such that neighboring vertices subsets intersect in exactly one element? Okay, so that's maybe a little bit hard to parse, but the answer is well known. It's called line graphs. So line graphs, the line graph of a root graph is the following. So I'm given some fiducial graph, and then the root graph, VE, is the following graph. Sorry, I'm given a fiducial graph R, VE, and is a graph L of R, EF, whose vertices correspond to the edges of R, such that 2 vertices are neighboring if the corresponding edges in R share a vertex. So let's do an example. Otherwise, I think this language gets confusing. So over here, we have two graphs. We have a fiducial graph and its line graph. So let me back up. So here we have a root graph, and I'm going to take the line graph of the root graph. And what that means is I'm going to associate vertices to these edges, and then I'm going to connect those edges when they're incident on the same vertex. Okay, so here's an edge in the root graph. Here's an edge in the root graph. They are incident on the same vertex, this vertex. So I put a vertex here, and I draw an edge between them. Okay, and then I repeat for every edge. So all of the edges in black of the root graph, so the root graph here is black, and the line graph is red and blue, right? So every edge gets associated a vertex, and the new vertices in red are adjacent when they are incident on the same vertex. Okay, so hopefully that example is clear. So now this is the line graph of my original root graph on the left, which was in black. Okay, so hopefully that example makes it a little bit clearer. Fundamental theorem is that there exists a generator to generator. This is our first theorem. There exists a generator to generator free fermion description of a Pauli Hamiltonian if and only if its frustration graph is a line graph. So this is spoken a little bit colloquially. I'll be a little more precise on the next slides. But the proof involves using a theorem from 1943 by Krauss, which just says it characterizes line graphs as follows. A graph is a line graph if and only if there exists an edge partition into cliques or complete graphs such that every vertex belongs to at most 2 cliques. So this is what we're going to use to build our fermion bilinears, this fact that there's 2 cliques. So here's a little more precise statement. Given this specific Pauli Hamiltonian, there exists an injective mapping that maps the Pauli terms specifically into fermionic bilinear terms such that the commutation relations are respected for the Paulis, if and only if this frustration graph of this Pauli Hamiltonian is a line graph for some root graph R. Okay? So one of these directions is sort of trivial. It's just that the definitions coincide. And the reverse direction just uses this Krauss decomposition, which is basically that we associate a fermion to each of these cliques in the Krauss decomposition, and we give the Pauli the fermions corresponding to its cliques. Okay? So let's do an example. So let's consider the path graph. So this is the graph with 3 edges. And the line graph of this, so I want to take the line graph. So that means this edge gets a vertex, this edge gets a vertex, this edge gets a vertex, and it just, there's only going to be 2 edges. So taking the line graph maps me over to this graph over here. So now let's see what happens if we, so no matter how an edge or edges is added to the interior here, something interesting is going to happen. We're always going to create a triangle. And adding an edge to the ends can only elongate it and just make this chain longer. So what happens now, let's look at what happens when we add something in the middle, right? Obviously, if I had added this edge on the edge, if I had added this vertex and the connecting edge over here, I've just made this path longer. Nothing very interesting just happens when I take the line graph. But if I add it here in the middle, right? So I have this sort of Y-shaped structure dangling. Now, this edge and this edge are both incident on this vertex. So I'm going to have to draw an edge connecting these 2 edges when I take the line graph. Similarly, if I had done it over here, I would get a triangle over here. Okay, this is inescapable. So it's impossible for a line graph to contain a claw. Okay, that's the point. It's impossible for a line graph to contain a claw. And so now, let's see, we had this interacting example that we spoke about before, where I added this ZZ interaction term to that pseudo XY ring. And you can see that there's a subset of the vertices that actually exactly form this obstruction here called the claw graph, okay? In fact, line graphs have a complete characterization in terms of so-called forbidden induced subgraphs. So forget about the fact that some of these edges are red. That's an artifact from me copying and pasting this figure from our paper. I'll describe why some of those edges are red in a little bit. But the point is the following, that a graph is a line graph. This is an independent characterization from Krauss's characterization. A graph is a line graph if and only if no subset of its vertices induces one of the following 9 forbidden subgraphs. Okay, so imagine I have a large graph with lots of edges, and then I just pick out a subset of the vertices and I delete all the edges that are incident to the vertices that I just deleted. Okay, so I just keep the induced subgraph. If your large graph has any one of these 9, or if and only if it has one of these 9 somewhere in its list of induced subgraphs, then it cannot be a line graph. Okay. So what this means, what this immediately implies, is that there's a polynomial time algorithm for checking whether or not something is a line graph, because you could just enumerate all of the subgraphs of bounded size. The largest one here has size 6. This would take time n to the 6th power or something, and then just check if any of them is on this list. So this gives you an efficient way to check whether or not something is a line graph. There's more efficient ways, which I'll talk about soon. But the point of this is that these are a list of obstructions for finding these sort of generalized Jordan-Wigner solutions to a spin model. This is like a complete list of interactions in some sense that obstruct a free fermion-solvable model. Yeah, which is what I just said. These 9 frustration structures are exactly the things that obstruct a free fermion solution, at least if you're restricting to Jordan-Wigner type transformations, linear transformations on fermionic modes. So that's kind of interesting. There's a few more things that come out of this characterization in terms of line graphs. So for example, there are certain isomorphism theorems that we can use to study the larger scale structure of these models by appealing to their graph structure. So with the sole exception of the triangle graph, so this graph here, the root graph of any line graph is in fact unique. So this specific graph, I can undo taking the line graph, and there's 2 different ways that I can take, if I started with this or this and I take the line graph, either way, I get this triangle structure. So this is the only graph that has a non-unique pre-image under this taking the root graph, taking the line graph, operation. So what this means is that a single qubit, do I say this on the next slide? Yes. I'll get into the implication of this on the next slide. Another theorem from 1966 by Jung says that if 2 connected graphs are edge isomorphic with more than 4 vertices, then they are also vertex isomorphic. And this vertex isomorphism is unique. So there's a small and finite list of graphs, which are exceptions to this isomorphism theorem, that basically edge isomorphism is vertex isomorphism, and moreover, it's unique. So what are some consequences of these theorems in the physics context? So from the first theorem, a consequence is that there is more than one way to free fermionize a single qubit. And moreover, that's the only time that there's a non-unique way to free fermionize a system. And we saw this actually in the Kitaev example. There's more than one way. Kitaev chose a specific free fermionization, but there's actually 2 different ways you can do it corresponding to this triangle, where I choose this mapping from spins to free fermions, or I choose this mapping, which induced these different commutation structures, right? So this would be the Hamiltonian, a general Hamiltonian for a single qubit, and it's free in a sort of trivial way. Kitaev does something interesting where he embeds these into the solution of this larger problem, but there's more than one way to do this. And this is the only case where there's more than one way to do it. Let me see how I'm doing on time. Okay, I'm going a little slow, but that's okay. I'll skip a few slides. So another implication is that, and I alluded to this already, line graphs can be recognized efficiently. Because of the forbidden subgraph characterization, there's a trivial algorithm that just enumerates everything and just checks brute force. But there are fast order n time algorithms that are basically optimal for recognizing. So what this means is, this means that you can, if you're given a specific Hamiltonian written out in a specific Pauli basis, you can check in linear time whether or not there exists a free fermion solution, even for something that's seemingly rather complicated. And then an implication of Jung's theorem is that Clifford symmetries, so by a Clifford symmetry, I just mean a Clifford operator that has, let me state it more. Yeah, so here's the colloquial way to say it. Clifford symmetries are necessarily symmetries of the fermions. So here's a free fermion Hamiltonian whose single particle Hamiltonian little h is in some fixed symmetry sector. Then any unitary Clifford symmetry that preserves the Hamiltonian induces a signed permutation symmetry on the single particle Hamiltonian, except for when U induces one of the three edge isomorphisms shown at right. So these are the exceptional cases to Jung's theorem that say when a vertex and an edge isomorphism aren't basically an identical thing, a unique and identical thing. So this is saying that global Clifford symmetries acting on the spins are also just symmetries of the single particle sectors themselves. Okay, so this is a strong characterization of the symmetries for these models. You can't have symmetries of the spin model that aren't also present as specific fermion symmetries of the single particle Hamiltonian, unless you're in a very small number of, a finite number of cases. There are also other types of symmetries that we call graphical symmetries or Pauli symmetries. So a Pauli symmetry, by Pauli symmetry, I just mean a product of Hamiltonian terms, Pj, that commutes with the terms in the Hamiltonian. So there can be products of Paulis that commute with the individual Paulis. So when might those arise? So we saw an example of that in the Kitaev solution when he took products of these links to build this cycle operator, and each of these hexagons then was a symmetry of the global model. So when do products of these terms give us symmetries of the overall Hamiltonian? So the subsets that arise as graphical structures, you can exactly characterize them, and there's exactly 3 of them, which I'll explain in a minute. There's something called twin vertices, cycles in the root graph, and the fermionic parity operator, and that's it. So we can solve, so in order to solve a general free fermion model, we would have to solve over each mutual eigenspace whenever you identify symmetries, which is exactly how Kitaev solves the honeycomb model, right? Whenever I have a constant of the motion, this symmetry operator can take the value +1 or -1. That's 2 different symmetry sectors. Generally, I'll have to, those are good quantum numbers. I have to pick a value +1 or -1, block diagonalize the Hamiltonian and solve it for each of those. So I guess a point there to make is that it's not necessarily efficient if you have an extensive or even a sub-extensive number of such symmetries. If you have k of these symmetries, then there's going to generally be 2 to the k symmetry sectors that you're going to have to solve individually. So you may need some additional physical insights to get a complete solution of the model when there's a large number of symmetries. Okay, so twin vertices. What are twin vertices? This is one of the 3, one of the only 3 possibilities that we can have for how these so-called graphical symmetries or Pauli symmetries arise. 2 vertices in the frustration graph that have the same neighbors, then if they have the same neighbors, then their product commutes with every term in the Hamiltonian. Okay, so these are what we mean by twins. We can remove these twins by fixing the corresponding stabilizer values. Let me give an example. So here's an example that we have. So this is, again, our XY model, but without, our pseudo XY model, but without the on-site Z terms. So what are some twins? Well, the twins are going to be 2 vertices that have the same neighbors. So let's pick these 2. So this term has x1 and x1, x2, and x3, x4 as its neighborhood. And y2, y3 has the exact same neighborhood. By this definition, that makes them twin vertices. Their product will, in fact, commute. And so, therefore, if I just look at the product y1, y2, y3, y4, it clearly commutes with x1, x2, right? Because y1, y2 commutes with x1, x2. And similarly, y3, y4 commutes with x3, x4. So I can assign plus or minus 1 to this product, and then I can delete one of these two vertices, and I'll get a smaller graph once I've fixed a specific symmetry sector and I've assigned this specific value to that symmetry. And I can iterate this, right? So now x1, x2, and x3, x4, they have the same neighborhood, namely y2, y3. So I can assign a symmetry sector eigenvalue to that, and then solve, again, a reduced model. And so now, this specific model is going to have two good quantum numbers plus this interacting term, which then I'd have to solve by free fermions. And I have to solve it over these 4 sectors to get the complete solution of the model. Okay, so whenever you're given this graph, you can find the twins and then iteratively delete the twins. The way in which you delete them doesn't matter, but you are picking a specific symmetry sector when you do it. Okay, in the interest of time, I'm going to skip the slide that describes how cycles and parity arise, because it's a little bit complex. But I'll leave it up so somebody can pause on YouTube and read the slide if they want. So, okay. There's one thing that I've glossed over here, which is the following. The sign of a term is changed whenever I exchange these labels J1, J2 in this isomorphism. So remember, how we're doing these mappings is we're taking each term in the Pauli Hamiltonian and we're associating fermion bilinears to it. But this choice J1, J2, this was kind of arbitrary, right? And I can flip the signs of these things by just exchanging these labels. Okay, so which choice of label is correct? Are they both correct? Is it non-canonical? How should we have been handling this sign information? This corresponds exactly to an orientation of the root graph. And it's not at all fixed by the commutation relations themselves between the Paulis. So we have to address this. So what we can do is we can choose the orientation whenever we fix these cycle symmetry eigenvalues. And the way we do it is the following. We can choose any spanning tree at all of the root graph. Once you've chosen a spanning tree of this root graph, we can orient the edges on this tree arbitrarily. And now we might be worried that when I try to close one of if there's cycles in the full root graph, I'm worried that I'm going to create some kind of weird frustrated situation where the orientations are not mutually self-consistent. So that's what we're trying to avoid here. We're going to orient the edges on the tree arbitrarily. This can't change the spectrum of H. It changes the eigenvectors by a diagonal plus minus 1 single particle matrix. So it's not really changing anything. For each edge not in the spanning tree, we can choose an orientation according to the sign of the unique corresponding independent cycle. So now when I add an edge, because this was a spanning tree, it's necessarily going to create a cycle. And then I'm just going to choose the correct sign to close that cycle, okay? And this is always self-consistent. So now let's put this all together and say, how do you solve a general Hamiltonian? Somebody presents to you with a spin Hamiltonian labeled in the Pauli basis like this. So the first thing you do is you check if the frustration graph is a line graph, and possibly by removing twins. So you iterate, you write down the graph, you remove all the twins by keeping track of some symmetries as you go, if necessary, and then you say, okay, is this a line graph? You can check that in linear time. If it's a line graph, then you find all of the Pauli symmetries, which we classified previously. For each symmetry eigenvalue configuration, we choose an orientation by first fixing a spanning tree on the graph, and then making all of the other signs self-consistent whenever we add edges to that spanning tree. Then we can solve the free fermion Hamiltonian with the resulting single particle transition matrix just by the standard Jordan-Wigner technique. We diagonalize the single particle matrix over SO2n, and then we restrict onto the fixed parity eigenspace if parity was one of the graphical symmetries that we identified, fermion parity, which I glossed over. So that's it. This is how you solve a general model. This is the most general solution for anything which is a generator to generator mapping. So, so this is not, this is the most general nearest neighbor 1D model with open boundary conditions that's solvable with this method. This is the frustration graph. So, here are the Pauli terms. You get XX terms, YY terms, and you get some cross terms that look like XY. Plus you get these on-site Z terms, Z sub J. So you can write out this graph and it looks like this. It's kind of messy, but then you check, oh, it's a line graph. Let's look at the root graph. So here's the root graph. We can identify a spanning tree. These red edges running down the spine here, that's in fact a spanning tree for this root graph. And then each of these edges, these black edges, is inducing some cycle. So we can orient this thing however we like along the red edges. We can choose self-consistent edge orientations for each of these black lines. And then we can associate fermion bilinears down the chain and just solve the model with the Jordan-Bickner transformation. The Kitaev model, similarly, we can do something similar. So we've got, here I've taken the root graph. So it's the line graph of this honeycomb graph. This is the frustration graph, rather. It's the line graph of the honeycomb graph, which is slightly confusing because the original model is defined on a honeycomb graph. But in general, these things are going to be different. These red edges, again, form a spanning tree. So we can solve it again using exactly this notion. There are other models that we can write down that are really complicated, that don't obviously look like they would have a free fermion solution. So one example is a 3D gauge color code. So with slightly modified terms. So I'm going to have products of x's around the hexagons, the cubes, and these little ball-shaped things. I'm not sure what those are called, but this convex shape that looks like that. And also z's. And the way that this is working, there's some commutation relations such that along these blue hexagons going this way, or the green ones going up, or the red ones going in and out of the page, each one of these is a mutually, so each chain is anti-commuting. It's an XY chain going coaxial through this lattice in each of the 3 cardinal directions. But the chains themselves all mutually commute with each other. So what this means is that this model here, this complicated looking 3D model, actually splits into a bunch of distinct XY models. So one for each of these coaxial chains of hexagon spin operators. And you can then solve this model exactly by mapping to disconnected XY chains. And this is a model that I've not seen in the literature before, that we call the Sierpinski-Hanoi model, because it's related to the Sierpinski triangle and the towers of Hanoi. So you can write down Hamiltonian terms that look like this. There are certain gauge degrees of freedom. I'm gonna skip over this a little bit quickly, but this model encodes logical qubits at some fixed asymptotic rate. You can solve this Hamiltonian by mapping it to free fermions using the tools that I've described in this talk. And you can, Adrian did this calculation and you can find the spectrum. Okay, there's one last thing that I want to talk about in the last 5 minutes before I leave it to questions. So Paul Fendley came up with a really interesting solution to something that he called free fermions in disguise. So he looked at a Hamiltonian that was translation invariant in 1D with open boundary conditions. He also looked at the periodic case, but let's focus on open boundary conditions. But the terms looked like this: Z, Z, X going down the chain. Okay, so these are 3-body terms and it's translation invariant on a chain. And these terms don't commute with each other. And if I write the frustration graph, they don't generally commute with each other. If I write the frustration graph, then it has this structure. This is just what it looks like for this example. And so Fendley solved this model. And he solved it by mapping it to free fermions. But if you look, this is one of the forbidden subgraphs that I described. Okay, so this is not actually a line graph. And as a witness, I give you that here is an induced subgraph, which was on the Beinecke list of 9 forbidden induced subgraphs. Okay, so what gives, right? Like, have I been lying to you? How is it possible that he was able to solve this when it seems to violate the theorem? And the point is that the mapping, so the theorem that I gave characterizes generator to generator mappings. So what this proves, the fact that there's this forbidden subgraph here, means that there's no mapping that takes the term zzx for each site and maps that specific term to a fermion operator itself, okay? Such a mapping doesn't exist. But that doesn't mean that there isn't something non-interacting in terms of fermionic operators that can solve the model. And the way that Fenley solved this model is he found a set of commuting conserved quantities, which he defined in this way by taking certain specific products of Hamiltonian terms. And he defined this transfer matrix in terms of some real parameter u. So this is like a polynomial in u that takes values over these conserved charges. He added one extra fictitious mode, which you can think of as a bit like a vacuum. And then he acts on this fake mode by the action of this transfer operator to generate sequentially, like it's like a ladder operator. It's giving you the rest of the fermions in the spectrum, okay? So I don't have time to go into any more detail about Fenley's solution, except that it was really tantalizing because it seemed to be a very radically different solution method that still nonetheless mapped things to free fermions, and it seemed to be very specialized to this specific chain. So what's going on here? Wasn't really clear. So I'm happy to report that in joint work with Sam Ellman and Adrian Chapman, we finally have an understanding of what's going on. So this set of conserved charges should properly be thought of as a product over independent sets of this graph. So the independent sets, in the interest of time, let me just say independent sets are basically like disjoint subsets of Hamiltonian terms. So we were able to prove that this Fenley-style solution can be generalized, again, to a graphical family of models. So all you have to do is study a Hamiltonian, write it down, and then check whether or not it has one of a list of forbidden subgraphs, claws or even holes. An even hole is like a cycle, but that doesn't have any chords connecting inside the circle, basically. So it's a circle with an even number of nodes in it, and there's no chords cutting through the middle of the circle, okay? So there's a forbidden subgraph characterization, and as long as your Hamiltonian's frustration graph doesn't have claws or even holes, then you can generalize this by building conserved charges out of independent sets. You can write down a transfer operator in a similar way to what Fenley wrote down, and you can solve these models whenever these conditions are met. So this is a new family of free fermion solutions that we can write down that are where we can really explore the entire phase diagram, because this solution method depends only on the graph. It doesn't depend on the detailed choice of coupling constants in the model. So we can really tune those coupling constants and study the entire phase. Okay, I'll wrap up here so that I have time for questions. So we've given a graph-theoretic characterization for a wide class of fermion-solvable, free fermion-solvable models. We've classified the symmetries in these models, at least in the free fermion case where we do a generator-to-generator mapping. There's a lot of open questions that remain. So if somebody hands you a local Hamiltonian, you might say, oh, but you've chosen a really poor choice of local basis that makes it look like they're interactions. But if I just rotate some of these qubits, I can do something analogous to curing a sign problem, and I can make this a free fermion-solvable model. So what if I give you the ability to do these local rotations? Can I still solve this problem efficiently? And we don't know the answer. We suspect that this is an NP-complete problem. It's in NP because if somebody just gave you, in the yes instance case, I would just give you the local rotations and then you can check that it's a line graph. So we suspect that this is NP-complete, but we don't know yet. these are some discussions I've had with Adrian Chapman and Dennis Stiegemann. There's also the case of translation invariant free fermion models. So in some joint work that I've done with Adrian and Alicia Kolar that should be on the archive, hopefully reasonably soon, we've studied the translation invariant case. And can we understand the translation invariant case without appealing to calculations that require modeling the full system size, but rather only look at the unit cell, right? So we want a kind of momentum representation where we don't really need to use an amount of data that sort of scales with the system size, but rather just focuses on a unit cell and really exploits that translation symmetry. Another interesting question is, there's another Fendley paper called free parafermions. And I think some of these techniques will probably generalize to the case of free parafermions. And I know that Adrian has some thoughts on that, although I don't know, you'd have to send him an email to find out what the latest is on that. I think that there are applications of these results. For example, to quantum impurity models, you might be able to do something like fitting to the closest free model. And you might be able to do something like find free fermion rank for Hamiltonians, decompose a Hamiltonian into a small number of free Hamiltonians and try to use this for things like variational quantum algorithms and things like that. I think there is a lot of scope for thinking creatively about the fact that there are lots of different ways to break up a Hamiltonian into a sum of disconnected free models, and then we can really test that efficiently. That's all. Thanks for your attention. Here is a list of references. So thank you very much.
Okay, so we have some time for questions. So because there's a large amount of people here, maybe either you can raise your hand or you could just start talking if you want. Okay, so Professor Viola.
Hi, Steve, so beautiful. I need to read the papers. I have a comment and a question. So you mentioned translation invariant systems, and just would naturally expect that if you want to look into those somehow, it would be natural to marry like tuplets, matrix structure, tuplets operators, and graph, because the translation invariance, we have recently studied, as you might have seen, like exactly solvable problems where we consider free systems which are translation invariant up to boundary conditions. And, and in that case, what turns out is like everything can be encapsulated into like suitable modifications of tuplets, banded block tuplets operators. So I would think, I don't know the math, but if there is a way to put together some clever graph stuff with those, that might be relevant.
That's really interesting. I mean, we're not considering boundaries at all in the translation invariant case. So if the tuplet arises from the boundaries?
No, tuplets capture the translation invariance.
Oh,
the
yeah,
boundaries for us, they go into corner modifications. So I don't know. That was just a thought that I had.
I see.
The question is, if, you know, I just look at your...
Oh, right, and it would be circulant if you had periodic boundary conditions.
Yes, correct.
Yeah, I got you.
Yes,
okay,
absolutely, absolutely. Yeah. If you were just given an operator, which is not necessarily a Hamiltonian, not Hermitian, but you are just presented like an expansion into Pauli, you would still be able to handle it? What does hermiticity afford here?
Oh, well, I think you need the hermiticity for the mapping to free fermions to work, don't you? Like if I allowed complex coupling constants in the XY model, can you still formally solve for the spectrum of that? Like, I mean, it seems strange to me.
Well, you have
it's
to
not
change
even necessarily
the
a normal operator.
what it might mean to be solvable, but there's plenty of stuff going around on non-Hermitian effective Hamiltonians and so on and so forth. And certainly there are ways to get exact results.
Well,
so,
let me try to think out loud a little bit when you say this. Like, you'd have to check that. I mean, the simplest thing to check would be like, look at the XY model or transverse field Ising model or something that's solvable by free fermions.
Yeah.
And can you formally allow complex coupling constants into that model and still find the eigenvectors and eigenvalues? I mean, it's not clear that it still has a complete set of eigenvalues and eigenvectors anymore, because I worry that you can create a non-normal operator if you do this. And if that's the case, then somewhere in that argument, the proof of a mapping to Jordan-Wigner is going to break down, because I mean, it might be that the single particle matrix that you get is also somehow singular, that the mapping still works, but that the matrix that you get is always also singular when you hit the singular case in the qubit.
Yeah, I was thinking to like.
But I haven't thought about how the mapping sort of factors through when you leave the nice world of Hermitian operators. It's an interesting question. But if you're just given
to forms, and so getting to canonical forms of something more complicated.
Yeah, I don't know. I would want to check a few examples before I said anything with.
Yeah, I agree. Thank you.
Thanks.
Any other questions? You can either unmute or raise your hand. So actually, I had a question. So when you consider the Kitaev Honeycomb Model, right, you basically found there are two possible mappings. But this is like a perfect Kitaev model, right? So if I consider like some lithium iodide, like a real world material, then sometimes we get this additional contributions. So we have a Heisenberg coupling, and we might have this off-diagonal symmetric exchange. So this complicates matters. And you can draw the phase diagram, and you can see, well, if it's perfect, if it's depending upon these parameters, like called J, the Heisenberg coupling and gamma, but this off-diagonal exchange, and then I might get like these 120 order ferromagnet, even a spiral order. So isn't there a way to basically consider how many free fermion mappings there are for general J, K, and gamma?
How many free fermion mappings?
Yeah, if there is any.
I mean, so you could certainly, for any given model, you can check whether or not there exists concretely a free fermion mapping that is of this Jordan-Wigner type, right? The generalized Jordan-Wigner type, where you map the individual Pauli terms to individual fermion terms, and then your solution is linear combinations of those fermions. Like, that's what I mean when I say a Jordan-Wigner solution. So the first theorem that I talked about is a characterization of exactly when you can do that. Is the graph, you write down the frustration graph, is it a line graph or not? So right there, I think you would find, as soon as you take the Kitaev, like the basic terms, and you add a Heisenberg coupling perturbation, I think you're going to find that you generate one of these forbidden subgraphs and you break the ability to create a free fermion solution. But it doesn't mean that that starting from the free fermion solution, applying that specific mapping, seeing where that Heisenberg term ends up in the mapping, like that might be a fruitful way to study it in perturbation theory. Like, it doesn't mean that it's, I don't know, like for those specific cases, I wouldn't know. But my feeling is it helps you identify like where's a good starting point. You start from the free model, you map it to the free degrees of freedom. You look at where the interactions get mapped to. Those are now perturbations on a free model. That might help you study the phase diagram. I can't be more concrete than that without understanding more of the model that you have in mind. And I may just not understand it, but that's, I think, a vision that I would have for how you would apply this.
Okay, thank you. We actually have a question in the comments. Maybe I'll read it. So Mayam Madasa asks, JW transforms from spin to fermions are non-local. Isn't there any way mapping to graphs can help us find geometric local mappings from spins to fermions for free fermion models?
Yeah, so that's a great question. I guess it comes down to how unique the mapping is. So, I mean, there's a lot of work that's been done on the locality structure of these types of mappings. So there's the Bravi-Kitaev transform, which you might know about, which I think has a locality of at most like log n when doing such a transform. I'm not actually sure what the most general answer to your question is. How you would enforce one mapping versus another mapping is good or better or best. But the literature to look at is, you look up fermion to qubit mappings more generally. So this just says whether or not one exists. It doesn't help you find the best one. So the literature on that, it goes under the name fermion to qubit mappings. Yeah, and I'm not an expert on this. The best one that I know of is this, from the perspective of the weight of the actual operators or the locality, is this, this is the weight only, not necessarily spatial locality, is this Bravi-Kitaev transform. But there may be others that I'm not aware of.
Okay. Okay, and he said, okay, thank you. Okay, any other questions? Like I said, either raise your hand or unmute. Okay, then you, Kai?
There's a question, yeah.
Hi, Steve. Thanks a lot for the great talk. So essentially, for given fermion, for given Hamiltonian, you find a way to kind of like recast it into the free fermion case. I see in the open question, you say something about try to fit into a free fermion model, which I assume is like for general Hamiltonian, you try to find like kind of the closest free fermion case, I assume, so that you can do perturbation on it and things like that. And you also mentioned something called free fermion rank. Does it mean that you can kind of view the Hamiltonian in some sense, some kind of superposition of free fermion, just like in a sense the stabilizer rank?
Exactly analogous to stabilizer rank. Yeah. So what's the smallest number of Hamiltonians, each of which is free fermion-solvable, such that a given Hamiltonian is a sum of these free fermion-solvable models? And you could put an epsilon on it and say, you know, I want to have some notion of an approximate free fermion rank, and so on. And yeah, I mean, I'm speculating, but maybe there are some ways to improve quantum simulation algorithms by taking advantage of this. You would need circuits that map you between these models, potentially. For the fit function, there's some work in the literature. I should have cited it here, and I'm blanking. I apologize to the authors that I'm not remembering their paper at the moment, but they've tried to find free fermion models that map to certain correlation functions as a way to try to say, well, okay, can I mock up certain correlation functions by building a free model that reproduces some given set of correlation functions? So you might try to fit at the level of correlation functions. You know, I was trying to be a little bit deliberately vague about what I mean by fit, because I think there's just a general open problem here about what that would even mean, how you would even approach that problem, what it would mean to be a good fit probably depends on applications. But like fitting something complicated by something less complicated, I think is a natural idea that I'm not really aware of a great general approach to solving that problem, but it seems like a great, pretty wide open question. And so if you have a good idea, you should try to make that precise, and it would be a really cool thing if you could do that.
Okay, thanks a lot.
Okay. So if not any more questions, maybe let's thank Professor Flammia again.
Thank you.
Thanks. Bye, everybody.
Thank you. Bye-bye. Good to see you.
You too.